So I'm going to stick to my pledge that you don't have to do the standard deviation stuff from like chapter 2. You guys remember that very first standard deviation table, x minus the mean squared and all that kind of stuff? Okay.
Do you have your office hours for this week?
They're on the...
Oh, okay.
Yeah, so while we're talking about that, if you look at your grade sheet summary, on the very top is the reminder about when the final exam is happening. And then in a little box here, there's my office hours during finals. So next Tuesday, no class. No classes. It's all finals. Monday, of course, is a holiday, so that's nothing happening there anyway. We don't meet again for class. We meet again for the final exam. You can come see me in the office, and I can see you then if you want to get some help. And those are my office hours. They're changing now because now I'm not going to be teaching. It's just the finals. And of course, I'm going to be in my office right before our final on the 4th. So we have our final on the very last day of finals. Yay. Okay. So, chapter 1, there was all definitions. Chapter 2, there was the stuff that I said we're not going to worry about. Chapter 3 is probability stuff. So we definitely want to worry about those. What was this guy? What was OR? OR was basically plus. OR was basically add. Why do I say basically add? Because you have to adjust it by doing what? Yeah, subtract anything that's both, because otherwise they would be counted twice. That only makes sense. Seems only fair. I like it. Does that sound familiar, hopefully? And then we had like probably A given B. What was that one? What was on the bottom? I love you guys. And then on the top, the only way that it could happen in A is if it happened in B, because B is what happened. So it has to be in A and B. So that's the given. Remember, these formulas get in the way, for the most part, when I have a situation where I can just count everything I need. So very often I won't use a formula at all unless I give you a problem like that one problem where I say P of A is 0.72 and P of A and B is 0.6. You got nothing except algebraic sticking numbers in and evaluate the formula, right? That's all you could do. Otherwise, I wouldn't even use these, to be honest. And then probably if A and B comes right off of this. So and is basically multiply. It's just adjusted a bit if the second dude depends on what happened in the first place. Okay. So behind this is the idea of mutually exclusive. Behind this is the idea of independent. Stuff you cannot write on your formula sheet. All right, so that's chapter 3, probability. And then chapter 4, we got into the x, p of x stuff. Right, so the little mean formula and the standard deviation formula. Comma sigma. Is that look familiar? Okay. And then we got into binomial stuff. Hopefully that looks familiar. All right, so many successes, so many failures. And then we got, with the binomial formula, we had our own, another mu and sigma. We always want to calculate those two. There's the most important way to summarize any set of data or distribution is what's the mean, what's the standard deviation. So for binomial, it was beautiful. NP and square root of NPQ, that kicks ass. I like it. You okay, Del? Yeah, okay. All right. So that's chapter 3, chapter 4. Chapter 5, 6, and 7 were all very much related. Chapter 5 was the uniform probability stuff, which I'm not going to write any formulas down. Don't even write the freaking mean and standard deviation formula. It ain't going to happen, all right? I'm not going to ask you a question about that. So uniform probability, you just have to remember how to draw it and how to figure out the height. All right? It's not that big of a deal. Or we'll find out. And then chapters 6 and 7 were all about normal distribution, z-score formulas, using the z-score chart. So we have the z-score, the basic z-score formula. We have the adjustment to that. We can put this one down. What's the situation when you would use this guy? This guy here. When I want raw scores, right? So if I have the raw score, I'm going to use this one. If I have a way to get a z-score, but I don't know what raw score that relates to, then this is what. So if I said, what IQ gets you into the top 5%, all right? So that I can get a z-score from the top 5%. They better give me this, and then I can figure out the raw score. What IQ score do you need? So it's the backwards. Normally I have a thing that I'm interested in what percentage is around this, and then I could make it a z-score and look it up. Or if they give me the percentage, the probability, I can look up that z-score and work it back. Change it back into an x-score. I like it. And then we had this. I still have people think that this is a ratio, but this is sigma sub x bar. This is the standard deviation for the sample means. And you might as well remind yourself immediately that even if it's s, you still have to change it, of course. Because sigma and s are both standard deviations for individuals. And if I'm talking about groups of things, I must change it to talk about groups of things. That's all that thing does. Okay?
Okay, so that one more time. So the S is when you're taking it to groups of things?
So sigma and s are both standard deviations for individuals. This is individuals from a population. This is individuals from a sample.
Okay.
This formula changes them into standard deviations for groups. How spread out are groups from each other? So like this part of the class versus that part of the class. I want to compare groups, then I better freaking use these, not the ones for individuals. That's really it. So everybody gets a little confused. Why'd you do this if it's already S? So that question makes no sense. Was it for individuals and I need groups? Oh shit, I better change it. Always. Okay, let's see. Yes, chapter 6 and chapter 7. Chapter 7 is the one that did this to us. Chapter 7 is the one about central limit theorem stuff. Oh shit, central limit theorem. What did central limit theorem say? We keep using one of its results all the time. The second step in hypothesis test for a mean. That helps us out, Jeff. First step is hypothesis. Second step is what are you going to use? How do you know if you can use a z-score? Well, you look at like the sample size to make sure it's bigger than 30. That's central limit theorem. Central limit theorem says if the sample size is bigger than 30, then the sample means will be normally distributed enough. Like that's why we do that step. Make sure that actually we could do all the stuff using normal distribution. All right, so that's chapter 7, 6 and 7. And then we get into 8, which is confidence intervals. And that makes sense. We built this, and this shows up primarily because now I'm talking about a group of things that I've taken a sample and I'm trying to figure out, get a feel for what the real mean is. Since I've taken a group of things, I have to use this new standard deviation. So it makes sense that immediately after this, I can then do the confidence intervals. So I've got these 3 formulas. The second one is the note that tells you when the hell to use a t-score, right? So if you say, I can use a z-score because I know the standard deviation, that makes no sense. how many standard deviations are there? Primarily, there are 2, right? Population standard deviation, sample standard deviation. And that's the key to knowing which one to do. Population Z, sample T. That's it. Right? This is your note telling you that fact. And then you have the one for p hat. This has p hat and q hat all over the place because we don't know what p is or q is. We don't know the population percentage. But later, when we did hypothesis tests, we don't have a hat on these because we're assuming we know what p is. It's the one from the claim. And along with these 3 confidence interval formulas, there are the ones for seeing how big of a sample I need to be within so much. So there was this guy. Oh, gosh. And this guy. Cool. So those are the main 5 formulas that come from Chapter 8, the confidence interval stuff. And then we get into hypothesis testing, which really doesn't introduce us to much new until we get to, like, well, you can put this down, I guess. This is the same formula, really, but put that down. And then we got the new one. This guy. Oh, it's for hypothesis test for percentage. Let's see. And, oh, you can put this down, T star. That's for 2 samples. And then, I mean, that's basically chapter 9 and 10 right there. Correlation, we didn't really have any formulas that we had to use. We just had to get them from the calculator and then use those. We can interpret those. Chapter, I think it was 11, with chi-square stuff. You can put this down. Hopefully all of that looks familiar. Is there anything I missed? It's always a possibility.
It's simple, but the p-hat formula.
It's funny that if you put this down, some of you guys are going to it's going to mess you up. But I almost don't want to put that down because it's just how do you make a percentage? You put the part divided by the whole. That's really all that says. It's a little true if you want to put that down. Anything else you think that you don't see up there? Like, I don't even remember half of those. I don't know the hell what I know what's missing. Yeah. Oh hell yeah. As I joke, you can bring in like one formula, one equation on a big piece of paper, and then another equation. As long as you don't interfere with anybody else, I don't give a shit. Yes.
And will you also? Is it okay if we do the lines and
Sure. Yeah. Yeah. Those are organizational lines. please, dear God, don't put anything else on there that I have to interpret as notes to yourself. I've had people do really interesting shorthand notes on things. No, it's just, just little marks. No, it's not. Yes?
What is this formula?
Oh, so remember, that's the one from chapter 2, when we had to make the tables for standard deviations. But now I'm just letting you do it in the list in your calculator. So that's the formula I said you only had to do in test 1 and never again for us.
And
Yeah.
the range, same thing.
All right, so I'll tell you this. The most I would do with like histogram stuff and all that kind of stuff is give you a histogram and you have to tell me stuff about it. Do you understand? I've got too much other stuff to ask you about to have time to make a histogram. I like it. If you want to, you could put down,
mid-range equals high plus low divided by 2.
Sure. The mean, if you don't have to calculate mean, I'll cry about that at some point. Okay. Let's see now. Let me make sure before I ask this question. Do I have... Yes, I have few. I have so few. Oh well. Anybody not get a practice final? That wants one? I've got 3. Everybody get a practice final? Okay. Cool. I like it. I'll give you guys the answer key in a bit. So now it's wide open. Whatever you guys want to focus on, we can focus on more recent stuff. We can go way back in time. We can Number 2, okay? So the numbers 348 and 259. 348 is on green paper. 259 is on red paper. I put them in a hat. I pick one piece of paper. What's the probability it's red paper? What's the probability it's red paper? It's number 2 on the practice final, which everybody said they had. So, say again? 3 out of 6, which is also 1 out of 2, which is also 50%. I like it. So there's a 50% chance. Half of them are red, so there's 50% chance. Probably is an odd number. Yeah, half of them are odd, so there's a 50% chance, right? These don't build on each other, by the way. It doesn't. So they're separate problems. Probably that I get a ticket that's green and even. It's got to be green and even. So how many tickets are even numbers on a green ticket? 2 out of 6. I love it. Why did the bottom not change? Because I didn't give you any information. It could still be any of the 6. It just has to be very specifically green and even for some reason, right? Even number given that it's on green paper. So now what's on the bottom? Because there's 3 pieces of green paper, and out of those, how many have an even number on them? 2 out of 3. So the only time the bottom changes, with not just reducing the damn thing, but the only time the bottom changes is if I give you information. That's when you can throw people or things out. You're like, well, you're not a part of this. Get out of here. I love it. Now, if I select 2 without replacement. Has everybody got what they want from this year? Yeah. What's up? Zoe, you have a question about?
Yeah, for C, why isn't it 3 out of 6 times 3 out of 6?
2C?
Yeah.
Okay, so let's look at that specifically. All right, I don't want to, please, dear God, I don't want to mess anybody up, but since we can count everything, I can do this without the formula. But the formula should match up with what we get, right? I agree. So 2C, it said green and even. There were 2 pieces of paper that were green and even out of 6 pieces of paper, so 1 out of 3. Now, the other way to do it would be green and even. What's probably it's a green piece of paper. The problem is it's not this, is it? It's probably green times probably even given green. That's the official formula. The second one is not keep it the same because it is dependent. It's not independent. You can't just multiply 2 probabilities unless you know that they're independent. So probably it's green is 3 out of 6. And probably it's even given that it's green is 2 out of 3. No. Given green. 3 pieces of paper are green. Was probably it's even 2. 2 out of 6, 1/3, same answer. I like it. That's why if you try to force the formula when it's a situation where you can just count, you're almost always going to get it wrong because you forget that the formula requires things to change if they do. If I could just count stuff, I don't have to think about this at all. I can just count and see it. I like it. And I have no idea what message you're taking away from that. It's really weird to hear a math teacher say, oh, the formula, don't use it. But the idea is more powerful than the formula is. So when I can apply the idea directly, hell yeah, I'm going to do that. Shit. But if I can't, then thank God the formulas exist. All right. Yes?
So I'm assuming we're using number 6, like the number 6 because there's 6 numbers. Because I remember before we used to add them up, but that's not the one that I'm thinking about.
So does that 3 mean 3 things? Where it says 3, 4, 8? Does that 3 mean 3 things? All right, read it.
So I said we put the number 3, 4, 8 on green pieces of paper and the numbers 2, 5, 9 on red pieces on red paper.
So how many pieces of paper do we got then?
3.
3 green and
So
3.
for each. So that's what it says.
Yeah.
I'm confused. I remember like when we did like.
No. You're thinking about 3, 4, and 8 as if they reference like 3 pieces of paper plus 4 pieces of paper. It's the number 3. It's the number 3 on a green piece of paper, 4 on a green piece of paper, and 8 on a green piece of paper. Yeah. So you've got to understand when the number represents number of things or when the number is a label. And in this case, the number is a label. I just wrote it on a piece of paper. It doesn't represent 3 things. So I have 3 green, 3 red, 6 pieces of paper. Yeah. Somebody asked about number, or was I about to get into number 2? Number 2, part 2. So now I'm picking 2 pieces of paper. Now again, if you wanted to, you could set up all the things that could happen from picking 2 pieces of paper without replacement, and then you can just, on site, create the probabilities. It's actually a little easier to use the formulas now. And I do this without replacement, so they'll probably get a red piece of paper first, nothing's happened, would be what? 3 out of 6? Then I throw that away. Right? So now they'll probably get a green piece of paper is 3 out of 5. There's still 3 green pieces of paper, but there's only 5 pieces of paper left now. Is that cool? And then you just work it out. 1/2, so I get 3/10. Okay, I like it. Same thing goes for part B. Why didn't the top here change again? It was because I didn't lose any greens. I just lost the red. If this was red and then red, then that top would have changed too. I like it. Yes?
Can we go back to way back to number 1?
Whoa! Okay, sorry. Okay, all right. Way back. Which one?
Like A and C.
Like part C?
1A and 1C.
1A and, okay. So 1A, if you read through that, 1A has to be nice. 1A is straight up normal z-score probability problem, right? That's it. I give you a mean. I give you a standard deviation. In fact, aren't those like for the population, right? It's awesome. And then if we select one U.S. adult and assume it's normal, because it didn't say it was, find that probability. So now you just got to make that into a z-score, look it up. It's greater than, so you got to do 1 minus, that whole thing. So you want to find that and do it. Because sometimes people just leave it blank because they did a few other ones and they're not even thinking that way. And they're like, what the shit? But you've got to know that. Holy shit, right? The normal z-score formula, you don't have to change any standard deviation. I like it. Part C, of course, is the one where you want to kind of draw it out first. I want what's P95 mean? 95th percentile, which visually would mean what? Yeah, okay. It's got 95% below it, so where am I going to draw the line? Over here. So this is 0.95. So this is a situation where I start by giving you the percentage. Normally the last thing is the percentage. But this is backwards. I give the percentage and I'm asking now for the amount of money spent on coffee. That would correspond to that. So what do you have to find out first? What can I go from probability? I can go directly to what? Z-score. That's what the Z-score chart does. Chart doesn't give a shit. If you know Z, it gives you probability. If you know probability, it gives you Z, as long as it's normal, and this one said normal, yeah. So you get the Z-score, and then how do you convert that back into money spent on coffee? What formula do you use? Well, you know Z, you know mu, you know sigma, which you don't know is X. So probably a formula to solve for X already. So this little dude here. So whenever I give you the percentage to start with on this kind of problem, you're going to have to work backwards. You're going to have to look up the z-score this way, and then you're going to have to put it into this backwards formula. This is the z-score formula I just solved for X. That's it. So, I don't know. Is anybody trying to look that up? 0.95?
It's 1.645.
Yep, 1.645. I like it. Because it's related to, this might freak you guys out a little bit. Let me see if anybody can follow me. What percentage is up here? If I draw a tail here and there's 5, this would actually be related to a 90% confidence interval. Do you have to do it that way? No. But some of you guys, when I say 90%, your brain goes 1.645 because you've done enough of the problems to remember. Some of you guys have done none of the problems, so hey, that explains a lot. And then you just plug that sucker in there with the mean and the standard deviation they give you. Yeah.
How do you do A? I'm really confused.
So 1A or 2?
Yeah, 1A.
Why did I put 2? Oh yeah, that was from something. 1A. So you draw, what goes right in the middle? No? Yeah, 164.71. And then where's 200 go? Yep. And I want greater than 200. Change this into a z-score. Look up the area. 1 minus because I want the above. So this problem is the bread and butter of statistics, really. That's why I say find it and do it. Make sure you get this right. So z equals 200 minus 164.71 divided by 3850. By the way, I've been using the same practice final forever. I think that's data from 1999. But it still works pretty good as a sample problem. I don't know if they can even track it anymore. Holy shit. Is that cool for number 1? What happens in part 2 on number 1? Yeah, but what's the nuts and bolts thing, the practical thing that happens? So do you notice how part 2A is the exact same question in one way at least as this one? But what's the difference there? I'm not asking x greater than 200, I'm asking x bar. So when I take a sample, in this case of 32, and I ask a question about the sample mean, what has to change? Standard deviation. I can't use the one that works for individuals and their amount of money they spend on coffee. I need the one that works for groups of 32 and how much a group of 32 will spend on coffee. So how do I change? What's the formula to change it? Yeah, it was 3850, so now we divide it by the square root of 32. And then I just do the same shit. I just put that new standard deviation there. It's always me minus the middle divided by the spread. But here, the first thing the spread does is change. And then, oh shit, I better put the new spread in there. And then the steps are the same after that. So this took me a while to cover the explanation. But the actual nuts and bolts of what happens is just really nice. Just change this, and then everything's the same as it was before. So now the z-score. So whatever the hell that is, same z-score formula is just going to have that new standard deviation in there, and then I'm going to look that up, get the area. Don't know if you want to try that. Go ahead. Yeah.
Do we have to do -1 for the mean also?
Yeah. No, not, well, all right, let's finish this out. So this problem, does anybody do this and get a z-score for this? For 1A? 1.34? All right, let's run with that. So if you look up 1.34 in the z-score chart, you'll get this area, but of course that's not the answer. You got to do 1 minus to get the other side. Now it's up to you to try to memorize that shit or just to draw the picture and go, oh, I got the wrong side. Let me do 1 minus to get the correct side. Some of you guys just kind of roll the die and sometimes you do 1 minus and sometimes you don't. Now you're just kind of doing it. You're like, I got to be right sometime. It's just, if you draw the picture and shade in the area you want, it will keep you anchored. It'll tell you when to make an adjustment. Yes? Same thing. So now, whatever this is, you plug that in here. That'll change the z-score.
And then you do 1 minus the z-score.
Never 1 minus the z-score. Never, ever, ever, ever. Because that doesn't make any physical sense. That would change where I am. So, Katie's looking like, well, then what the hell then? I remember you saying 1 minus shit, Jeff. Tell me. What's the area you get when you look at 1.34?
I think it's wrong though because I think it runs to 92. So it has to be.
All right. Oh, well, holy shit. Yeah. All right, guys. Did you see me check that with anything? So, I asked, and one person said the z-score, 1.34, that's wrong. What should that z-score be? 0.92. Yeah, okay. I'm crowdsourcing the damn thing, right? If you did it and you got a different answer, speak up. Nobody says shit, I'm going to say, oh, 1.34 must be right. So if you look up 0.92, yes, I love you guys. Everybody got 0.92 sitting there like, what did I do wrong? And you just didn't speak up. That's what you did wrong. Yeah.
Why are you using 38.50 there? Because that's the original.
Yes, yeah, because this is 1A. This is 1A.
Oh.
Here's 2A.
Yeah.
That's where I'm changing the standard deviation. Okay. All right. So now if I look up 0.92, I'll get this area below, because that's all the chart understands. I think I've given all my z-score charts away, so. Say again?
0.8212.
8212. And so to get the other side, you have to do 1 minus that. What's happening, guys? What's up? You guys all right? All right. So if I have a problem where I give you the mean and the standard deviation, say it's normal, and he asks you for probabilities greater or less than something, you make a z-score and look it up in the z-score chart. Of course you do. Right? If it's normally distributed, it's what we've done forever. This is the bread and butter of this course. So here they tell me the mean is 164.71. Standard deviation 38.50. So I can graph this problem. I can draw a picture for myself. Are you guys hung up on somebody telling me the wrong z-score? Is that what hung up about? Let go of that shit. So if I calculate the z-score, I get 0.92. That's the z-score for it. I can get the area below that z-score, but the problem wants the area above. Okay, so if I look up 0.92, what area do you get? 8212. Okay. Now, is everybody with me so far? Okay, this has desperately got to be
Now you do 1
an
minus?
easy problem. Say again?
Now you do 1 minus?
Yes, because now it makes physical sense. Where's that 1 come from in the 1 minus? What's 1 got to do with anything? Because the whole picture is 100%, so that's 1. So doing 1 minus the z-score makes no sense. What's special about the z-score of 1? It doesn't make any sense. And if I do 1 minus z-score, I change where I am. I can't change where 200 is. If this is 164.71, 200 is right there. I can't go, no, I want 200 down there. No, you can't do that shit. So it only makes sense to subtract areas. You never, ever subtract z-scores from each other, from anything. So now up here will be 1 minus 0.8212, which is 0.1788. That's weird.
Careful, we can be able to read your answer.
I don't know. It's up to you. I don't know what you want from me. Okay, and everything we just did is exactly the same for 1-2A, except you just use the new standard deviation. So you make a z-score from that new standard deviation. You don't divide by 3850, you divide by whatever this is. Look it up, get the area below, do 1 minus to get the area above. Same steps. We could look at anything you want to. Anything.
The 10.
Oh, 10 was the... Oh, okay, yeah. That's the hypothesis test about a percentage. So if you look at number 10, can you identify the claim?
P is greater than 0.387.
Yeah, so the claim is we feel it's increased from previous years, and previous years it's been 0.387. So the claim is P greater than 0.387. Anybody here have like 3 finals in the same day?
Heck yeah.
Okay. Anybody else? 2 of you. Okay. I don't think that deserves a duh. 2 of you have 3 finals in the same day? Okay. Okay. Let me see. Thankfully, I don't this time around. You take a survey, 292. Okay. So which one is this going to be? HO or H1? Yeah, because it has no equal sign in it. And then this will be old HO, then the...
Less than or equal.
Yeah. And some of you guys put equal to, that's fine, because the book does that sometimes. So this is going to be a 1-tail or 2-tail test?
2.
2, because it's got a direction, right? Greater than. I only care about that side. So 1-tail test.
Oh, what is equal? It's 2.
Yeah, equal, not equal to. So not equal to, there's 2 ways to show that. Greater than, there's only 1 way to show that. All right. What do I check for a probability problem, percentage problem, to see if it's normal enough? What do I check? So what do I check to see if I can use z-scores? NP and NQ. Notice you didn't use hat, which is perfect, because I know what P is. 0.387. We're just going to assume it's that number. That's how hypothesis tests work. Assuming it's that, look what I just did. That's basically what hypothesis test is all about. So what's N? 292, so it would be 292 times 0.387. And this would be 292 times, what's Q? $613. Yeah, just 1 minus this, of course, as always. And so whatever you get for those, and it's got to be greater than 5, which they will be. Did anybody get something for those? Blah, blah, blah. And so this will be 179, blah, blah, blah. That's why I make somebody say blah, blah, blah. I did it, yay. So they are both bigger than 5, so that means that this is normal enough, which means I can use z-scores. What if one of them or both of them were less than 5? What would you do then? You stop. I love it. Exactly. You don't use t-scores. T-scores don't mean shit for MPQ problems. T-scores were invented with stuff about means. They don't come into play here at all. I love it. But on the test, I want you to do every problem. So remember, there was one problem where somebody said, I won't do anything, and then they did it. And the reason you keep going is you might overlook somewhere in the problem. I say it's normal enough, or something, you just overlook something. So to be on the safe side, just do it. So we can use z-scores. So what's going to tell me how to set up the rejection region then? By the way, do you see how on number 10 I don't give you the steps? I don't think I gave you the steps anywhere, did I? Ooh, I'm really evil. I love it. But on the actual final, I'll at least give you the steps once. And then you just always reference. It's the same steps every time, right? Just give you different alphas. Let me see. So rejection region. What's the alpha in this one? Yeah, 0.09. I'm using z-scores. Is 0.09 an area that's on the t-score chart? No. So I have to do it the old-fashioned way, right? So one-tailed test, it's going to be up here. This is going to be 0.09 here. Can you figure out what that z-score is? What are you going to look up to see what that z-score is? 0.91. Because that's the only thing the chart understands is areas below the z-score. So if you look up 0.91, what do you get? Here's, well, it's freaky. Somebody earlier said one. Now it comes into play. So if z star is greater than 1.34, that matches with the shaded part. We can do what? We can reject the hope, support the high. I like it. You still going? Yeah.